In this video, we're going to talk about the one concept that distinguishes calculus from every math class that's prior to calculus, and that is the concept of a limit. So in calculus, there are really three big topics that you talk about. There are limits, derivatives, and integrals. But derivatives and integrals are both defined in terms of limits. So the idea of a limit is the foundational concept of what calculus is all about. So what is a limit? Well, I think the best way of understanding what a limit is all about is using an example. But let me just say, first of all, that the idea of a limit is the idea of getting closer and closer to, or approaching. So when you hear the word limit, think closer and closer. So what is a limit? Well, let's consider this particular function here, f of x. And it has the formula x squared plus x minus 6 over x minus 2. And there are various questions we could ask about this function. For example, what does the graph of the function look like? But we could also do things like plug in values. So for example, we could ask, what is f of 4? Right? If we want to find that, we just plug in 4. So f of 4 is going to be 4 squared plus 4 minus 6 over 4 minus 2. Okay, and if we work this out, this is going to be 16 plus 4, which is 20, minus 6, which is 14. So we get 14 in the numerator. And then 4 minus 2, we get 2 down here in the denominator. And 14 over 2 simplifies to be 7. Okay, so f of 4 is 7. Now what this means graphically is that the ordered pair 4 comma 7 is on the graph of this function. But nothing all too interesting happened here. We just found f of 4 by plugging in the value 4. Now we're going to get something much more interesting if we plug in the value 2. Okay, so what is f of 2? So 2 is going to be kind of a special value for this particular function. So what is f of 2? Well, f of 2, if we do the same thing here, we get 2 squared plus 2 minus 6 over 2 minus 2. And so in the numerator, this simplifies to be 4 plus 2, which is 6, minus 6, which is 0, and 2 minus 2 is 0. So we get 0 over 0. Now the question is, though, what is 0 over 0? Okay, 0 over 0 is something that's going to occur over and over again for us. But what does it mean? What is 0 over 0? I thought anything divided by itself. So for example, 3 over 3, isn't that 1? But also, isn't it true that 0 divided by anything? So for example, like 0 over 5, isn't that 0? Okay, so what is 0 over 0? Is it 1? Or is it 0? Or is it something else? Well, it turns out that 0 over 0 is undefined. It's sometimes called an indeterminate form. In fact, anytime you have 0 in the denominator of a fraction, that fraction is going to be undefined. So what this really means is that 2 is not in the domain of the function. Okay, but where limits are going to get involved here is if we ask not what do we get if we plug in 2, but what do we get if we plug in values that are close to 2? Okay, so what if we plug in numbers that are close to 2? So what if I wanted to find f of 1.999 or f of 2.001? Okay, what kind of output would we expect? Okay, now I want you to think about this. Maybe, in fact, you can even pause the video here and just think about it for a second. What type of output do you expect? If we plugged in, say, 2.001 for x here, here, and here, and simplified this, what would we get? Would we expect a number maybe that's close to 1? Or maybe something that's close to 0? Or maybe since when you plug in 2.001 down here in the denominator, you get a tiny number, maybe this whole fraction kind of blows up and you get a really huge number, like 1,000 or 1,000,000. Well, it turns out actually none of those things happen. All right, well, I've pulled up the online graphing calculator Desmos, D-E-S-M-O-S, and you can just Google Desmos or go to desmos.com and get to this graphing calculator. I really love this online graphing calculator, and I think it would be helpful for you to get familiar with it as well. So one of the things you can do, for example, is type a function in f of x equals x squared, let's say, and notice it'll graph the function over here. Now, we're going to type in our particular function, but we're not really going to be interested in what the graph of the function looks like just yet. So let's type in f of x equals, and let's put a division symbol here, x squared plus x minus 6 over x minus 2. Okay, and it'll graph it over there, but again, let's not worry about what the graph looks like just yet. One of the things we can do, though, is say, what is, for example, f of 4? And notice it gives us the answer here. F of 4 is 7, just like we calculated earlier. Now, we could also plug in, let's say, f of 2. And notice, again, f of 2 is undefined, just like we talked about. Remember that f of 2 ended up being 0 over 0, but 0 over 0 is undefined. Now, let me pull this up a little bit so we can see better here. What about, though, if we plug in f of 1.9? Well, notice our output is 4.9. Okay, what about 1.99999? Well, notice our output is 4.99999. Notice our output is really close to 5. Now, what if we plug in something a little bigger than 2, so like 2.1? Well, notice we get 5.1. Or 2.00001. Well, notice we get 5.0001. So again, notice that when we're plugging in inputs that are close to 2, our outputs are close to 5, right? And that might be a little bit unexpected for you, right? Why are we getting 5 as an output? We'll talk about that in a little bit here. Why is it 5? But I just want you to notice that for this function, when we plug in 2, it's undefined. But when we plug in values that get closer and closer to 2, our outputs get closer and closer to 5. Okay, so I've kind of summarized this in a table of values here. So we plug in different values of x and figure out what is f of x. Notice f of 2 is undefined, but we plug in these values that are close to 2. We're getting these outputs that are close to 5. Now, what we say is that the limit as x approaches 2 of this function f of x is 5. So this little x with the little arrow to 2, the way you say that is x approaches 2. So we say the limit as x approaches 2 of this function is 5. So what that means is as our inputs get closer and closer to 2, our outputs are getting close to 5. Now, we could also write it like this, so we actually have the formula in here for our function f of x. So the limit as x approaches 2 of this function here is 5. Now, again, you might wonder why it's 5, and we'll talk about how you calculate limits a little bit later. So here we just plugged in values of x that were really close to 2, and we got outputs that are close to 5. We'll talk about how you can calculate it in a better way than that. So basically using some algebra to be able to figure out that the answer would be 5. But for right now, we're just trying to understand the concept of a limit, right? As these inputs get close to 2, these function values, right, the outputs that we get when we plug in those values get close to 5. Okay, and I put it on the screen here in words. The limit as x approaches 2 of f of x is equal to 5. That's how we read this notation here. Now, in general, we write this. So for some general function f of x, and some number c and some number l, we write this notation, limit as x approaches c of f of x equals l. We write this to mean if x gets close to c, but not equal to c, then the values of f of x get close to L. So in other words, as x gets closer and closer to c, right, as x approaches c, these function values get closer and closer to L. Now, one thing I do want to point out is that the limit does not depend on how the function is defined at that number c, but only how it's defined near the number c. So if we go back up to our example, notice that at 2, the function was undefined, but that really doesn't affect what the limit is. In fact, how the function is defined at 2, it could be defined to be anything. It could be undefined, or it could be defined to be 17, or it could be defined to be 5, right? It actually doesn't affect the limit how it's defined at 2. What matters is as these x values get close to 2 without equaling 2, what are those f of x values getting close to? And they're getting close to 5. In fact, let's look at this little table of values here that I made for some function f. Now, I don't have a formula here for this function f of x, but this is not the same function f that we were looking at just a second ago. So this is just some other function f. But let's suppose the function has this table of values. So notice as my inputs here are getting close to 8, right? So I have 7.9, 7.99, and so forth. We also have 8.1, 8.01. As my inputs are getting close to 8, what are my outputs getting close to? Well, notice it looks like they're getting closer and closer to 13. So what we say is that the limit as x approaches 8 of f of x is 13. So this answer would be 13. Now notice I did not define it here at 8. The function could be undefined at 8, or it could be defined to be something else. It could be defined to be 4. Okay, well, if it's defined to be 4, that still doesn't affect the limit. Now notice in this case, f of 8 would be 4, but the limit as x approaches 8 of f of x would still be 13, because the limit does not depend on how the function is defined at that number 8. Okay, right, f of 8 in this case is 4, but the limit as x approaches 8 is 13, right? As these inputs get closer and closer to 8 without actually being 8, those outputs are getting closer and closer to 13. Now, I should point out that for most functions, or for many functions, what you end up getting at something like this, at 8, would actually be 13 itself. Okay, in this case, what we'd say is that the function is continuous at 8. So in other words, f of 8 is 13, but as the inputs approach 8, the outputs are also approaching 13. So if you just kind of randomly write down some formula for f, this is what's most likely to happen. And in fact, in this case, the idea of a limit is not even really all that important or relevant because f of 8 is 13, but as we approach 8, we're also approaching 13. Where limits kind of come into play more often is when we have a situation where it's defined to be something other than 13, or in fact, if it's undefined. In fact, this is the most common case that we're going to run into where limits are actually important, is when the function is actually undefined at 8. Right, so that was like our previous example that we looked at. We had the function undefined at a certain point. So notice, again, the limit as x approaches 8 of f of x, in this case, is still 13. It's unaffected by how the function is defined at that number 8 itself. Now let's do one more example here. What's the limit as x approaches 49 of x minus 49 over the square root of x minus 7? Well, notice if we were to just kind of plug in 49 itself, right? If we thought of this as our f of x, if we plugged in 49 itself, notice we'd get 0 on the top. We'd also get 0 on the bottom, right? The square root of 49 is 7. 7 minus 7, 0. So if we just plugged in 49, we'd get 0 over 0, which is undefined. But what this is asking is not what do you get when you plug in 49, but what do you get when you plug in values that are close to 49? Let's go back to Desmos here again, and let's type in our formula for our function. So f of x equals, and we'll put our division symbol, and we're going to put x minus 49 in the numerator, and the square root of x, so you type just sqrt, and it gives you a square root symbol, square root of x, and then minus 7. And so what we're going to ask is, first of all, what is f of 49? Well, f of 49, notice, is undefined. But that actually does not matter as far as the limit is concerned. As far as the limit is concerned, we're not interested in what is f of 49, but what is f of values that are close to 49. So what if we type in like 48.999? Well, notice, what are our outputs close to? They look like they're close to 14, right? 13.999 something. Okay, what about if we plugged in 49.01? Okay, or 49.0001. Well, notice again, our outputs are also close to 14. And in fact, the closer we get to 49, so if I do 49 point, add a couple more zeros here, the closer our outputs are getting to 14. Okay, or if I add a couple more nines here, well, notice as my inputs get closer and closer to 49, the outputs are getting closer and closer to 14. So what we'd say over here is that this limit is 14. Okay, so we provided some kind of numerical evidence that the limit should be 14. Now, again, we're going to talk about how you actually calculate a limit like this without actually plugging in values that are 48.999 or 49.001. How could you actually calculate this limit using some algebra? How could you figure out that it should be 14? We'll talk about that really mainly in the next video. But one other thing that I'd like to point out about this particular example is let's actually look at the graph of this function. Let's scoot over here. One of the things that Desmos does not do too great is this function actually has a hole in it. So actually, if you go to 49 here, Desmos doesn't actually show the hole unless you drag right on top of it. So notice that at 49, the function is undefined there. When you plug in 49, you don't get an output, so there's a hole in the graph. Okay, and you can only see the hole if you drag over it. Now I'm going to do some trickery with the formula and make it actually show the hole right here. But notice here what's happening, right? At 49, so 49 is right here, the function's undefined, but what if we're plugging in these values that are close to 49? What if we plug in, let's say, 48.5? Well, notice the output is close to 14, is 13.96, right? If we plug in something a little bigger than 49, like 49.5, the output is 14.0 something. Now at 49 itself, it's undefined. Okay, there's a hole in the graph there. But the question is really, how high is that hole? And the hole is right up here at a height of 14. So there's a height of 10. It's actually at a height of 14 is the height of that hole. So as x approaches 49, as the inputs approach 49, the outputs of this function are approaching 14. Even though when you plug in 49 itself, you don't get an output. It's undefined there. Okay, let's go back and look at this example that we saw earlier here, where we were trying to find the limit as x approaches 2 of this. Now remember, when we plugged in 2 itself, we ended up getting 0 over 0, which is undefined. But when we plugged in values that were close to 2, we ended up getting outputs that were close to 5. And so this limit ends up being 5. Now the question is, though, where does this 5 come from? It's kind of mysterious, right? Why do we ended up getting 5 right here? Well, that's what I want to explain right now. So suppose we have this function f of x equals this formula here, x squared plus x minus 6 over x minus 2. And let's simplify this formula. And by simplify, what I mean is that we can actually factor the numerator. So x squared plus x minus 6, that factors. And the way that it ends up factoring is x minus 2 times x plus 3. So you can check for yourself. If you FOIL this out, if you multiply it out, you end up getting this, right? X times x gives you the x squared. You have a minus 2x by multiplying these inside two terms. You have a plus 3x from the outside two terms. So that minus 2x plus 3x becomes a plus 1x. And minus 2 times plus 3 ends up giving you the minus 6. So if you FOIL this out, you get this. Okay, well, notice that we have an x minus 2 factor occurring in both the numerator and the denominator. So what we can do is cancel that factor. Okay, so this simplifies to just be x plus 3. Okay, or could we, right? Were we supposed to cancel that factor? Could we actually cancel that factor? Is this the same as this for all values of x? Well, it turns out that this is the same as this for all values of x except x equals 2. If you plug in 2 right here, this becomes 5. Whereas if you plug in 2 for x here, you end up getting 0 times 5 over 0. But 0 times 5 over 0, the zeros can't cancel. You end up just getting 0 over 0, which is undefined. But any other value of x, these two expressions are the same. So when I put equals here, it's really equals for all values of x other than x equals 2. And in fact, if we think of this as our f of x here, so this whole function here is our f of x, which has this formula, which is exactly the same as this formula. And if we think of this as being, let's call it g of x, let's say this is g of x. Okay, g of x is x plus 3. F of x is this formula, or which is the same as this formula. Are f and g the same function? Well, they're almost the same. Okay, f of any value is going to be the same as g of that value, with the exception of x equals 2. Okay, g of 2 will be 5, whereas f of 2 is undefined, right? It's 0 over 0. Now, graphically, what's happening here? If we look at the graph of these, well, what's the graph of g of x look like? Well, isn't that just a straight line, right? It's of the form mx plus b, where the m is 1, right? The slope is 1. The b, which is the y-intercept, is 3. So this is just, the graph of this is just a straight line with a y-intercept of 3 and a slope of 1. In fact, let's graph this here. We have a y-intercept of 3 and a slope of 1. So here's a y-intercept of 3. Every time we go over 1, we go up 1. The graph's going to look something like this. Okay, this is the graph of g of x. Now, what about the graph of f of x? How is the graph of f different than the graph of g? Well, they're actually the same graph, with the exception of the fact that at x equals 2, it's undefined. So you actually get an open circle here on the graph of f. So the graph of f is basically just a straight line with a hole in it. Okay, but if we're trying to find what's the limit as x approaches 2 of this function here, of this one here, it'll be the same thing as the limit as x approaches 2 of this function, where this function has the filled in hole. Because remember, the limit doesn't have anything to do with how the function is defined at 2, only how it's defined near 2. And near 2, but not equal to 2, f and g are the same function. So they should have the same limit. So basically, when we're trying to find the limit as x approaches 2 of this f of x function, we can just find the limit as x approaches 2 of the g of x function. And the way we can find that is essentially just by plugging in the 2. Okay, it's a nice enough function that it doesn't even have a hole anymore. So we can actually just plug in 2, and that will give us the correct answer for the limit. So we'll talk about computing limits in the next video. But the reasoning behind why this limit ended up being 5 was because when we simplify this, we cancel these x minus 2 factors and plug in 2 now, plug in 2 for x at this point, we end up getting 5 as a result. So hopefully that solves a bit of the mystery about where that 5 comes from. In fact, if you want to see the worked out details of how you would actually compute this limit, you'd say, well, this is equal to the limit as x approaches 2 of, and then what you do is factor this, and again, it factors to be x minus 2 times x plus 3. and we have this x minus 2 factor still in the denominator. We cancel these, and we say that this is equal to the limit as x approaches 2 of just x plus 3. And now at this point, this is a nice enough function that you can find the limit essentially just by plugging in that number, even though technically the limit does not depend on what the number is that you plug in, only numbers that are near the number. Well, it turns out this is a nice enough function. You can just plug in the number that'll give you the result. Whereas the original one had a hole in the graph, right? It had a hole in the function where 2 was. Okay, so we just plug in 2, we end up getting 2 plus 3, which ends up being 5. So that's how you'd actually compute this limit without plugging in numbers like 1.999 or 2.001. But again, we'll talk more about computing limits or evaluating limits, it's sometimes called, in the next video. So let's look at another example. And this one is maybe not quite as interesting, but it's pretty simple here. F of x equals x squared plus 1. And the question is, what's the limit as x approaches 3 of f of x? Now, is this the same as asking what is f of 3? And it turns out it's not the same thing. To ask what's the limit as x approaches 3 of f of x is not the same thing as asking what is f of 3. Now, in this problem, you're going to get the same answer, but it's not really the same question. Okay? The question is, if x gets close to 3 but not equal to 3, what does f of x get close to? So let's look at a graph of the function. So here we have a graph of the function x squared plus 1. And notice that if we plug in 3, we get an output here of 10. Right? That order pair 3 comma 10's on the graph. So f of 3 is 10. So, but the question is, though, what's the limit as x approaches 3? So if we plug in like 2.9, okay, what's our output going to be? Or if we plug in 3.1, what's our output going to be? Well, I made a little table of values here, and we plug in values that are close to 3, like 3.001. Turns out we get 10.006001. Or if we plug in 2.999, we get 9.994001. So notice that when we plug in values that are close to 3 but not equal to 3, we get values of f of x that are close to 10. Now, it turns out that f of 3 is also 10. Okay, but that actually has no bearing on what the limit is. It could be that we got 15 right here, and our limit would still be 10 as long as these values are getting close to 10 as we approach 3. Or this could even be undefined, and the limit would still be 10. So again, the limit does not depend on how the function is defined at that number, at 3, only how it's defined near the number. Right? As these inputs get close to 3, the outputs get close to 10. Okay, so we say that the limit is 10. So based on both the table and the graph, we can say that the limit as x approaches 3 of this function is 10. And in this example, we also had f of 3 being 10. So we have this limit as x approaches 3 of f of x ends up being the same as f of 3 in this example, but that's not always true. Is it always true that you can find the limit by just plugging in that number? You can find the limit as x approaches 3 of f by just plugging in the number. It turns out you can't. It's only true if f is what's called continuous at c. And we will talk about continuity a little bit later. Okay, so let's look at another example. Here we have a function that's a piecewise function, so it has 2 different formulas. So one formula if x is not equal to 1, another formula if x equals 1. So notice we could say, what's f of 1? Well, f of 1 would be 5. But then we could say, like, what's f of 9? Well, we have to ask ourselves, is 9 equal to 1 or is 9 not equal to 1? Well, 9's not equal to 1, so we have to plug in 9 here. If we plug in 9 here, we get 11. So f of 9 would be 11. Okay, now what does the graph of this look like? Well, the graph is mainly going to look like x plus 2, right? X plus 2 looks like this, right? It has a y-intercept of 2, slope of 1. But it's going to have a hole in it, right? Because when x is 1, it's not going to be defined to be 3 like we'd expect it to be. It's actually defined up here at 5. So the graph of this function looks like this. Now, what we could ask, though, is what is f of 1? Well, notice f of 1 is 5, right? Either based on this or based on the graph, we can see f of 1 is 5. What's the limit as x approaches 1? What if we plug in values that are close to 1? Like, okay, 0.9 or 1.00001. What are our output values going to be close to? Well, those output values are going to be close to 3. So this limit is equal to 3. Well, notice the limit as x approaches 1 of f of x was not the same thing as f of 1. Okay, f of 1 was 5. The limit, though, was 3. Okay, so these two things are not the same. They're not asking the same thing. This is asking how is the f defined at 1. This is asking how is f defined near 1, but not equal to 1. Okay, let's look at another example. And this one, I've called it f, but we don't have a formula for this function. And one thing you could ask about this is this really a function? Does it pass the vertical line test? And it turns out it does. Every vertical line you draw is only going to intersect this graph at most at one point. Even this vertical line, it only intersects the graph there. It does not intersect the graph down there. There's a hole in the graph. Okay, so let's answer these questions. What's f of 1? Well, notice f of 1 is not way up here. F of 1 is actually just 3. Now, what's the limit as x approaches 1? Well, if we plug in these values that are close to 1, notice our output values are going to be close to 7. Okay, so the limit as x approaches 1 of f of x is 7. Now, what's f of negative 2? Now, nothing really all that interesting is happening at negative 2. Notice f of negative 2 is 1, but also the limit as x approaches negative 2 of f of x is also 1. So if we plug in something a little to the left of it, like negative 2.1 or negative 1.9, which would be a little to the right of it, notice our output values are close to 1. Okay, so here, the function is actually continuous, so we have the same value here for how f is defined at 2 and how it's defined near 2. Okay, now what is f of 4? Well, over here, f of 4 is 5. But what's the limit as x approaches 4? Now, you have to be a little careful here. So it kind of depends on whether we're on the left side of 4 or if we're on the right side of 4. Now, if we're plugging in a value that's a little bit less than 4, like 3.999, we're getting outputs that are close to 2. But if we plug in values that are a little bit bigger than 4, like 4.001, we're getting outputs that are close to 5. So we're not getting close to one particular number. We're kind of getting close to two different numbers. And so what we say here is that the limit does not exist. And the way we write this is DNE. The limit does not exist. Essentially, it's because, well, we're going to talk about what's called a left-hand limit and a right-hand limit. The left-hand limit is not the same as the right-hand limit. So I'll say what that means in just a second here. But notice as x approaches 4 from the left, right? If we're letting our x values approach 4 from the left, f of x approaches 2. But as x approaches 4 from the right, f of x approaches 5. Okay, since those values are not the same, since 2 and 5 are not the same, the limit does not exist. Okay, but what we can say is that it does have a left-hand limit and a right-hand limit. And the way that we write that is like this. Limit as x approaches 4 from the left. So this minus does not mean minus 4. We still have a positive 4 here, but it means that we're approaching 4 from the left. We're taking values a little less than 4, like 3.999. As we approach 4 from the left, the values of f approach 2. So the left-hand limit is 2, but the right-hand limit is 5. And we put a little plus here to indicate we're approaching 4 from the right. This doesn't mean plus 4. It is plus 4 here, but the plus here means we're approaching 4 from the right. Okay, as we approach 4 from the right, we got 5 as our limit. Okay, now the ordinary limit, the original type of limit that we were talking about, sometimes called the two-sided limit, exists if and only if both the left and right hand limits exist and have the same value. So now notice the left hand limit exists and the right hand limit exists, but they don't have the same value. So the ordinary original two-sided limit does not exist. Okay, let's look at one more function here. Let f be this function. Okay, what is f of 2? Well, notice f of 2 is down here at minus 1. Okay, what is the limit as x approaches 2 from the left? And again, this is positive 2, but we're approaching from the left. Well, as we approach 2 from the left, our outputs are really close to 3. They're approaching 3, so we get 3. As we approach 2 from the right, though, our outputs are approaching 6. And so what about the ordinary limit, the two-side limit? Well, again, this limit does not exist because the left and right-hand limits are not the same. Now, if these two had been the same, so let's say this had been 6 and 6, well, then the two-sided limit would exist. The ordinary limit would exist, and it would equal 6, even if this is still negative 1, or maybe even if this doesn't exist. As long as these two things are the same, the left and right-hand limits are the same, then the two-sided limit will be the same, okay, and that have that same value. Okay, now a question you could ask is, what if we have a function like this where it doesn't even have a formula? But the one thing that we know is that the limit as x approaches negative 2 from the right is 13, and also the limit as x approaches negative 2 from the left is 13. What can we say about the ordinary two-sided limit? Well, that would also be 13. Okay, because these two values both are 13. That would even be the case if f of negative 2 was some other value, so like 7, or maybe it didn't even exist. We would still get 13. All right, one question we could ask is it possible for left or right-hand limits to not exist? Notice in this previous example that we did, even though the ordinary limit did not exist, we still had that the left and the right-hand limits existed. So could we have a function that is weird enough that not even the left and right-hand limits exist? And so I've gone into Desmos and I've graphed this function f of x equals 1 over x minus 3. And notice it has a vertical asymptote there at 3. So notice, in fact, I can even write it in as x equals 3, a vertical asymptote. Let me make it a dotted line here. So notice, what's the left and right-hand limit as we approach 3? Well, as we approach 3 from the right, if we take inputs that are a little bit bigger than 3, so like 3.1 or 3.01, notice we're getting huge outputs. We're getting outputs that blow up to infinity here. So as we approach 3 from the right, the limit does not exist because it's blowing up. In fact, later we'll talk about infinite limits, and it turns out as we approach 3 from the right, this limit is infinity. Now, the limit doesn't exist. Just because we say it has an infinite limit doesn't mean the limit exists. The limit doesn't exist, but the reason it doesn't exist is because it's blowing up to infinity. Okay, and as we approach 3 from the left, if we plug in numbers a little less than 3, it's going down to negative infinity down here. Okay, so the limit as x approaches 3 from the left is going to end up being negative infinity, but it doesn't exist. So here's one way that a limit couldn't exist at a left or right-hand limit couldn't exist at a number. Another way is if we take a function like this, sine of 1 over x. Now, you may or may not have seen the sine function before. It's a trigonometric function, but sine of x is kind of a weird function. Or sine of x is actually not too weird, but sine of 1 over x is a really weird function. Sine of 1 over x looks like this. Notice it actually oscillates back and forth infinitely many times in here. You can keep zooming in. It just oscillates infinitely many times. So it's kind of impossible to draw this by hand, really. But what's the limit as x approaches 0 from the right? So 0 is right here. As we approach 0 from the right, well, notice it's not blowing up. Okay, but the limit doesn't exist. The reason it doesn't exist, though, isn't because it blows up to infinity. It's because it's oscillating back and forth so that it doesn't approach one particular number as we get closer and closer to 0. And same thing with the left-hand limit. The left-hand limit will also not exist as we approach 0. So there's a few different ways that limits cannot exist. Left and right-hand limits cannot exist as you approach a particular number. Okay, so you might wonder, what do limits have anything to do with the real world? This all seems well and good for these functions that we see on paper, but what does this have anything to do with reality? So let me give you an example. So earlier today, I was driving in my Bentley on the highway. And by the way, I'm just kidding. I don't have a Bentley. But I was driving in my Bentley on the highway. You can just go with this. And I was trying to figure out, okay, how fast am I going? So I looked down at my speedometer and I noticed, oh, it doesn't have a speedometer in this car. Apparently, it's a very cheap Bentley. But I realized, though, oh, I can figure out how fast I'm going right now because I know that over the last 2 hours, I've driven 140 miles. So that means I'm going 70 miles per hour. But then I thought, well, wait a second. That doesn't tell me how fast I'm going right now. That just tells me my average speed, my average velocity over the last 2 hours. If I've driven 140 miles in 2 hours, that means I've averaged 70 miles per hour. But I could have been speeding down, slowing up. Of course, I know I was going faster than that at certain times, slower than that at certain times. There's always some guy in the left lane, some idiot driving 53 miles an hour in the left lane. And I know I wasn't going exactly 70 the whole time. So how can I figure out how fast I'm going right now? Well, then I thought, okay, well, maybe if I look at the last 1 minute instead of the last 2 hours, and I know how far I've traveled in the last 1 minute, I could figure out how fast I'm going right now, however many miles I went and so forth, and divide that out. But the problem is, again, that only gives me my average velocity over the last minute. If I want to figure out how fast I'm going right now, how do I do it? Well, I could look at the last 1 second. Surely that would tell me how fast I'm going right now at this instant. But again, you have the same problem. I could have been slamming on my brakes or speeding up in that 1 second time interval there. So that only gives me my average velocity. So you might think, well, why don't I just take the last 0 seconds? But the problem is the last 0 seconds, I've traveled 0 miles or 0 feet or 0 inches, however you want to talk about it. So if I actually try to figure out how fast I'm going based on the last 0 seconds, I would have to divide 0 by 0. And of course, that's undefined, just like we had our function earlier where we were dividing 0 by 0, and that didn't make sense. So you can't figure out your velocity by looking at the last 0 seconds, but you also can't figure out how fast you're going right now looking at the last 2 hours or the last 1 minute or the last 1 second or even 0.001 seconds. So how do you figure out how fast you're going right now? Well, you need to use a limit. you take the limit as the amount of time approaches zero. And then you look at your distances that you've traveled in those times, and those distances will also approach zero, but that ratio of the distance over the time, and you take the limit as that time goes to zero, that will give you your instantaneous speed, your speed right now. So anytime you're talking about a rate of change, like a speed, or a rate of change really of anything, limits are involved. Okay, so limits actually are important and valuable in real life situations.